What would you do if you had the power to change your destiny? Imagine a cold night without a moon, with a dense fog in the air. As you cross the road, the fog swallows the sounds and the headlights of the approaching car. Before you realize it, it's too late to avoid the impact. Suddenly, an unknown man pushes you out of the way, saving your life, but sacrificing his. Later, a police officer hands you an envelope found in that man's pocket. It's addressed to you. Upon opening it, you find a note with just 2 words: study physics. Intrigued, you decide to follow the advice of the person who saved your life at the cost of his. Decades later, you become a renowned physics professor, specializing in Albert Einstein's theories. You've always felt that time travel was possible, and one day, you finally unravel the mystery. The world's first time machine stands before you. That's when everything makes sense. How did you not realize it before? With the letter kept all these years, you enter the time machine, adjust the controls, and go back to that cold, foggy night. You arrive in time to push your younger self out of the car's path. You die on the road. It seems simple, but that's where things get interesting. Who wrote the letter? Do you, in the future, simply take the letter you received as a teenager and go back in time? The letter exists without a creator, trapped in a temporal loop. This is the bootstrap paradox. And these temporal loops, do they keep repeating? You save your teenage self, who grows up to travel back in time and save your teenage self, perpetuating an infinite cycle. But what about the letter? Does it age and wear out? This is the restoration paradox. Where did the idea to study physics come from? The notion seems to come from nowhere, a thought without origin, the ex nihilo paradox. If these events can really happen, then you never had free will. You would always invent the time machine, with no option to do otherwise. This is the predestination paradox. And what if you change your mind? For your older self, this is not an option. You can't hesitate and let your younger self get hit by the car. This is the self-infanticide paradox. It's impossible to kill a younger version of yourself, even by doing nothing. Welcome to the strange and fascinating world of time travel. Traveling freely through time seems impossible, right? But there are loopholes in physics that suggest possibilities. If time travel were possible, how would we do it? Imagine the scenario. The sun is shining brightly, birds are singing in the forest, and the river's current carries you without needing to paddle. Have you ever thought about what it would be like to float in time like this? Jack Finney, one of the masters of time travel fiction, compared our experience of time to this river. We are relentlessly carried from the past to the future without effort. But what about the parts of the river we've left behind? Where do our yesterdays go? Does the past simply disappear? It seems absurd to think that a river would vanish just because we turned a corner, right? The parts of the river upstream are still there, even if we can't see them. And what about the future? It seems to magically appear when today ends, but where does it come from? Science reveals that time is like a river, already traced from the Big Bang to the death of the universe. Past, present, and future coexist. Philosophers call this eternalism, the idea that everything exists simultaneously, as opposed to presentism, which says only the now matters. For physicists, eternalism is known as the block universe theory, supported by Einstein's general theory of relativity, one of the most revolutionary in the history of science. In 1905, Einstein published the special theory of relativity, eliminating Newton's absolute time. There is no universal clock. Time is relative, depending on motion through space. One observer might see an event before another, while another might see the opposite, and both are correct. An event in your past could be in someone else's future. How could our yesterdays disappear if they are still in others' tomorrows? Moreover, special relativity shows that space and time are not separate. In 1908, Hermann Minkowski combined space and time, creating the concept of space-time. And how do we know they are really together? The proof came with Einstein's general theory of relativity, presented in 1915. Think of space-time as the surface of a trampoline. place something heavy in the center, and it sinks, creating a gravitational well. Einstein showed that gravity is an illusion, an effect of the curvature of space-time. Planets move through this curvature, not by gravitational attraction. Mercury, for example, has its orbit altered by the extreme curvature near the Sun. Since then, experiments have confirmed Einstein's theory, showing that our universe is a block of space-time where past, present, and future coexist. And where did all this come from? From the Big Bang, which created all space and time. In the block universe, all regions of time are there, from the past to the future. Objects in the block universe have spatial and temporal coordinates, forming world lines. You are a collection of these lines, moving through space-time. All your actions from breakfast to marriage are mapped. The block universe is like a book, with a beginning, middle, and end already written. Every choice is predetermined, like a character who doesn't know the outcome, but it's already there. In a remote region of the universe, a gigantic, supermassive black hole dominates an entire galaxy. The intense gravity of this black hole is pulling, stretching, and tearing apart entire solar systems. Hot gas and dust swirl around it, while its enormous magnetic field accelerates and launches debris into the void of space. In the midst of this chaos, a tiny particle, a proton, races through the cosmos at nearly the speed of light. Can you imagine that? This proton has 100 quintillion times more energy than a common light particle, and after traveling more than 1 billion light-years, it collides with Earth's atmosphere with an absurd amount of energy, 21 million times more than the collisions in CERN's Large Hadron Collider. When these cosmic rays hit our atmosphere, the impact is so violent that it explodes in an invisible fireworks display of subatomic particles. Pions, muons, and neutrinos burst forth and scatter to the ground. In fact, cosmic rays are so abundant that they give us an annual dose of radiation equivalent to 3 chest X-rays. An Italian physicist named Bruno Rossi became obsessed with these cosmic rays. His pioneering work with muons, created by these rays, provided some of the first evidence that traveling into the future is not only possible, but common. Imagine Rossi at the wheel of an old Jeep, winding his way up the highest road in the world. Cedars compete with snow-covered mountains to reach the sky. Eventually, he arrives at Lake Mirante in Chile, high in the Andes, nearly 7,500 feet above sea level. In the mountains, Rossi is measuring the muons created by cosmic rays. Muons are unstable particles that decay quickly, but Rossi's measurements reveal something intriguing. Many more muons are reaching the ground than they should. Why? Einstein's special theory of relativity gives us the answer. When something moves very fast, like muons, less time passes for it than for us. For the muons, fewer half-lives have passed, so there simply wasn't enough time for 99.9% of them to decay. This effect is called relativistic time dilation. But you might wonder, does this really count as time travel? Let's think of a different scenario. Imagine you are a muon, but instead of traveling from the atmosphere to Lake Mirante, you travel around the universe at 98% the speed of light and return 25 years older. For us on Earth, 125 years would have passed. This is pure physics. Traveling to the future is more than possible. We just need to accelerate humans to near light speeds. But the faster you travel, the more energy you need. Einstein's famous equation, E=mc2, tells us that energy and mass are interchangeable. So the faster you travel, the heavier you become. To an outside observer, a person traveling at 99.99%, the speed of light would weigh nearly 2 tons, the same as a hippo. And there is another form of time dilation, gravitational time dilation. Imagine a clock made of 2 horizontal mirrors with a light beam bouncing between them. If you take such a clock to the bottom of a gravitational well, space-time will be more curved, and the clock ticks less frequently. Bringing it back, more time would have passed on the clock that wasn't in the well. But how can this be used for traveling into the future? enter a deep gravitational well, and then return to Earth. More time would have passed here than for you. However, for this, you would need a very deep gravitational well, like a supermassive black hole. This idea was explored in the movie Interstellar. Even Earth creates its own gravitational well in space-time. When Rossi climbed the road, he aged slightly faster on the mountain than at the base. Although the difference is small, atomic clocks can detect it. In 2022, physicists measured this gravitational time dilation with clocks placed just 1 millimeter apart. And finally, you probably use time dilation without even realizing it. GPS, essential for modern life, depends on it. Satellites orbiting Earth send time signals, and the clocks on board need to be adjusted to account for time dilation. These experiments make it clear that traveling to the future is possible. But what about traveling to the past? That's another story. In 1937, a young man named Willem Jacob van Stockum showed that Einstein's equations allowed for closed time curves in space-time. This means that, in theory, you could revisit past moments, such as your birth, or even save your teenage self from an accident. But to do this, it seems you would have to go faster than light, stepping out of what we call the light cone. But what if we could tilt that light cone? In 1974, physicist Frank Tipler suggested that a gigantic cylinder, spinning at insane speeds, could warp space-time enough to tilt its light cone and allow time travel. But this cylinder would have to be infinite and spin billions of times per minute, something we can't achieve with current technology. In the 90s, Stephen Hawking brought more complexity, saying we would need vast amounts of negative energy to make this work. And here comes quantum mechanics, which deals with the subatomic world where particles appear and disappear all the time. Negative energy exists, but only in small areas for short periods. Another interesting idea is wormholes. In 1985, famous astronomer Carl Sagan asked his friend Kip Thorne for help with his book, Contact. Thorne suggested that Sagan use wormholes for space travel. Imagine space-time as a piece of paper. If you fold the paper, the ends meet, allowing instant travel. Thus, a wormhole could take us to distant places or even to the past without violating the laws of physics. But wormholes have a problem. They tend to close. We would need something to keep them open, like negative energy, or perhaps quantum entanglement. In 1985, J. Richard Gott and William Hiscock showed that cosmic strings could be used for time travel, tilting their light cone backward. Thinkers like Stephen Hawking and Igor Novikov discussed these ideas. Hawking suggested that traveling to the past is impossible, while Novikov believed that you can't change the past. But if each trip creates a new timeline, then quantum physics gives us a way out of these dilemmas. Bryce DeWitt and John Wheeler, two big names in physics, also explored these ideas. DeWitt talked about how each quantum transition creates new universes, while Wheeler, despite initially supporting the idea, eventually found it metaphysically heavy. Still, the many worlds interpretation has gained adherence over the years. Did you enjoy this journey through the quantum world? Leave your comment and share your crazy theories with us. And don't forget to like and subscribe to the channel. See you next time.